Welcome to this video on Year 2 Pure Chapter 9 Part 2 on differentiation of inverse trig, parametric equations, use of implicit differentiation and related differentiation or related rates of change. Question 1. So for this question you need to be aware of the results that the differentiating inverse or arc sine, arc cos and arc tan, there are standard results. You might be expected to know how to obtain these results, but most importantly, you need to know the results, some of which you'll find in the formula booklets. So the derivative of arc sine of x is 1 over the square root of 1 minus x squared. The derivative of arc cos of x is the same, but with negative sign in front. And the derivative of arc tan is 1 over 1 plus x squared. Question 2. A function is concave if the second derivative is negative or has a maximum 0. So you can think of the curve being curved concave like this, and so that the gradient is decreasing, and so the second derivative is negative. Similarly, it would be convex if the curve was like this, and the second derivative was greater than 0 or possibly equal to 0. Question 3. Here's an example of a parametric equation, and we want to work out dy dx. And to work out dy dx, we use the chain rule. So dy dx will be dy dt dt dx, which can be rearranged to dy dt divided by dx dt. So we differentiate y to get 2t plus 5, and then divide that by the derivative of x, which is 6t squared. And if we divide those out, we get this expression here for the derivative dy dx in general, and at t equals 3, the derivative will be obtained by substituting t as 3 into the expression for dy dx. Notice the dy dx we're getting not in terms of x or y, but in terms of t. This is one of the consequences of using parametric differentiation. Similarly, for question 4, we're asked to work out the gradient of the tangent to a curve. Now, the gradient of the tangent is the same as the gradient of the curve. So effectively, it's the same as question 3. We've been asked for dy dx at the value of the parameter being pi over 3. So we get dy dx is dy d theta. The parameter here is theta rather than t, over dx d theta. We work out dy d theta by differentiating 4 sine theta to be 4 cos theta. We get dx d theta by differentiating 3 cos theta to be minus 3 sine theta. And then if we divide these out, we get 4 cos theta over minus 3 sine theta, or minus 4/3 cot theta. And then at theta is pi over 3, we get this gradient here, which is the gradient of the curve and also the gradient of the tangent. Question 5. Now we come on to implicit differentiation. The key thing with the implicit differentiation is that we don't work out dy dx directly. We simply differentiate the equation of the curve given implicitly, usually for this course, by differentiating every term with respect to x. And that way, dy dx will emerge. So differentiating the x squared with respect to x, we get 2x. Differentiating 2x with respect to x, we get 2. Differentiating y cubed with respect to x, we use the chain rule to differentiate it with respect to y as 3y squared, and then by the chain rule we must multiply by dy dx so that we obtain the rate of change of y cubed, not with respect to y, but with respect to x. In other words, we're differentiating everything with respect to x. So the 3y squared is how fast y cubed changes with y, and 3y squared dy dx is what we want, which is how y cubed changes with x. And then to differentiate 2xy, we use the product rule. We leave the 2x alone and differentiate the y to get dy dx. And then we leave the y alone and differentiate the 2x to get the 2. And so we obtain this. And then the next stage is to isolate all the terms that involve dy dx on one side and all the terms that don't involve dy dx on the other side. Factorize out the dy dx, and then we have an expression for dy dx in terms of x and y. And this is very typical of implicit differentiation, that we have the gradient dy dx in terms of x and y. So we need both the x and y coordinates to work out the gradient of the curve at a specific point. The gradient doesn't depend only on the x coordinate or on a parameter as we found earlier, but depends on both the x and y coordinates. So for question 6, if we now want to find the gradient of the curve at 1, 3, we go through the same process of finding dy dx and then substitute in x is 1 and y is 3. In differentiating this expression, notice that the first one here is a product, so use the product rule, differentiating x squared minus 1 and leaving the e to the 3x alone, and then the other way around, leaving the x squared minus 1 alone and differentiating e to the 3x to get 3 e to the 3x. And then for the second expression, y squared over x, we use the quotient rule, squaring the x squared, leaving the x and differentiating the y squared with respect to x, which means we differentiate with respect to y, multiplied by dy dx, and then we subtract differentiating the x and leaving the y squared alone. And then last of all, differentiating 3y with respect to x, we get dy dx. And as before, we write every term that involves dy dx on one side, the terms that don't involve dy dx on the other side, and then rearrange by factorizing and dividing to get an expression for dy dx. Quite complicated in this stage. We could simplify, or we can simply substitute x is 1 and y is 3 as we do here, and obtain an expression for the gradient of the curve at the point 1, 3. Question 7, to find the point of inflection of a curve, we first of all need to find out when the second derivative of the curve is 0. This gives us candidates for points of inflection. So differentiating once, we get f dashed of x, and then using Lagrange's notation, f double dashed of x is when the second derivative is 0. In this case, we get a quadratic, which has two solutions, x equals 1 and x equals minus 2. And if we want to know the coordinates of the points, we substitute x is 1 into the original to get y is 46, and x is minus 2 to get y is 1. And these are two candidate points for points of inflection. And then to see if we have a point of inflection, we can use a variety of methods, one of which is to work out the third derivative, put in r1, and put in r minus 2, and we see that in each case, the third derivative is non-zero, which means that the second derivative is changing, so that it is 0 at 1 and minus 2, but it's changing through those points. And because it's changing, that means we do have a point of inflection. An alternative way of showing that it's changing is to find the second derivative of nearby points and see that it's going through 0 at those points, but on one side it's positive and the other side it's negative. Either way, we have shown in this case that both the points 146 and minus 2, 1 are points of inflection. The first method of working out the third derivative and substituting those values in is the more usual method. And then the last question, question 8, is related rates of change. If you read through the question, you find that you have a formula for V in terms of R, volume of a sphere in this case, and then the surface area in terms of R, the surface area of a sphere in this case, and then we're given a rate of change. The volume is increasing at the rate of 0.1 meters cubed per second, and then we want to know the rate of increase of the surface area when the radius is 0.4. The general pattern of these questions is to realize that you're given one rate of change, dv dt, and you want to work out another rate of change which is related in some way. In this case, we want to work out dA dt. And what we usually do is write down the rate of change that we want, dA dt, the rate of change that we know, and try to write down the rate of change that we want in terms of the rate of change that we know. So using the chain rule, we want dA dt, and we know dv dt. So we want to cancel out the dv because that's not involved in what we want. So we put a dv at the bottom, and we want a dA at the top. So we put a dA there. And then we look at the equations to see if there's a relationship between A and V directly, and there isn't. We could combine these equations to get one, but it's actually easier to find a variable that links them up, which in this case is R. And so we say dA dv is dA dr, dr dv, where you can see the dr's cancel. And that means that we can get a chain of rates of change that will give us dA dv. So dA dr we can get by differentiating A with respect to R, and differentiating 4 pi r squared with respect to R, we get dr is 8 pi r. And similarly, if we want to get dr dv, we more easily find the dv dr by differentiating v with respect to r, which gives us dv dr is 4 pi r squared. And that then means that what we want, which is dr dv, not dv dr, is the reciprocal of 4 pi r squared. So dr dv will be 1 over 4 pi r squared. And so dA dt will be the product of these three rates of change. dA dr, which we calculated to be 8 pi r, dr dv, which we calculated to be 1 over 4 pi r squared, and dvt, which we're given as 0.1, which means that dA dt will be 0.2 over r, or 1 over 5r. And only at this point do we need to use the fact that we're interested in the rate of increase of the area at a specific value of r, which is 0.4. We substitute that r is 0.4 here, and we get 1 over 2 meters squared per second, or 0.5 meters squared per second, which is the answer that's required. Okay, so it looks complicated, but hopefully, if you follow the process indicated here, you should find these reasonably straightforward, as long as you can find formulas and do the appropriate differentiation. Okay, I hope that was useful.